we saw in the last video what to do if one of the values is a constant. But now, what if one of the components is linear? In that case, what you're going to do is stretch the graph into whatever dimension has that linear component. You'll see when I draw it. Okay, so we have, in this particular one, you can see that we have a linear component right there. So we are going to stretch it in the upward direction. All right, now what are we stretching? Well, let's look at the other two components. Those should be setting off little bells in our head. We know what 4 cosine t for sine t looks like. That's a circle of radius 4, and it's counterclockwise. All right, now how are we going to draw that? So it's a circle that's getting stretched. So let's think about where it's going to start at t equals 0. Now, it actually doesn't start, if you will, at t equals 0, but I'm just going to give myself a starting point at t equals 0. There's no restriction on my domain here, so I can kind of do whatever I want. So I'm going to start with t equals 0. R of 0 would be 4 cosine of 0, 4 sine of 0, 0, which would be 4, 0, 0. Okay, well, I know where that is. 1, 2, 3, 4. It's right there. So that point right there is 4, 0, 0, which is when t equals 0. This, of course, is the vector. That's the point. The vector points to that point. All right. Now, I'm also going to think about it a little bit later. It's not an ending point. I just want to think about this. What would r of 2 pi look like? That would be 4 cosine of 2 pi, 4 sine of 2 pi, and then 2 pi, which would be 4, 0, 2 pi, or about 6.28. So that would be up here. 1, 2, 3, 4, 5, 6, 6.28, so it'd be like right about there. So up here is t equals 2 pi, just for the heck of it. All right, so how do we draw this? Well, you start here at this value, just because you need a starting point. You could technically be anywhere. And you're going to spiral up and around to this point. You start here and go up. And of course, there's nothing particularly special about what I'm doing, so you could keep going. You could keep going up and up and up. So what are we drawing? Badly. What we're drawing is a spiral, right? It's like a spiral staircase. So this is a spiral, aka a helix. That's the fancy name for it. Yes, there is some difference between the two, but for our purposes, we're just going to call them the same thing, right? All right, so this is a helix. All right, that's a circle stretched in a linear direction. So when you take a circle and you stretch it, you're making a helix. Now, the easiest ones to draw are ones where it's a single value, like in this case, z equals t. So it's just a straight line going straight up. Or y equals t would go straight that way, x equals t would come out towards us, which is hard to draw, but it's a spiral, so you just kind of do loop-de-loops. All right, what if it's not it's a straight line, but it's not one of the coordinate axes? Well, then it's okay. It's still doable. It's just a little bit trickier to draw. Hold on, I gotta find my page. Here it is. Okay, so we can see the linear component is right here. So x equals 2 minus t. So it's going to be, that's our linear component. And so it's going to stretch in a negative direction. Or for our purposes, let's just think of it. Stretch along a diagonal line. All right. That'll work for our purposes. Again, we do most of this with computer programs. We don't do this by hand. Actually, I don't know what I'm thinking. It's not the diagonal line. Let me just say it this way. It's in the negative t direction for x. So let's just say stretch along the x direction. Let's just leave it at that. We don't need to get more specific than that. Okay, but what are we stretching in the x direction? Or negative x direction, which is where this one would go. It's actually technically in the negative x direction because it's x minus t. All right, well, it's an ellipse, right? If we look at this 3 cosine and 5 sine, and we put those two together, that's an ellipse. That's y equals 3 cosine of t, z equals 5 sine t. So that's an ellipse that's counterclockwise. And it's taller vertically, because that's a 5 in front, than it is wide. All right, again, let's give ourselves a starting point here, just someplace to start with the drawing. So let's give ourselves maybe a couple points. So if I put in r of 0, I would get 2 take away 0, 3 cosine of 0, 5 sine of 0, which would be 2, 3, 0. Well, I know where that is. If I go out 1, 2, and over 1, 2, 3, or if I take 3 in here and I put it on a diagonal, it's right there. So that's my point at t equals 0. That's 2, 3, 0. All right. And so then we're just going to draw a helix from there that goes around counterclockwise and is taller than it is wide. And so on. It's not perfect, but I'm doing my best. All right, so, and I need to have arrows on it because I have to show orientation. It's moving counterclockwise, right? So it's kind of easiest to show it at the tops here, right? As it's working its way around that helix. All right, how about one that's doing something completely different? So down here, oh, before I go there, let's check me with Maple. Sure enough, there you go. It's a spiral, right? Again, Maple can't show the arrows, so you have to know that that motion is there, but it's going around and around. Now, it doesn't look like an ellipse because of the axes here. If you look at the top axis, or the vertical axis, it's -5 to 5, but this side is only -3 to 3, so it's not actually drawing it in a way that looks like an ellipse, but it is an ellipse. That's a scaling issue. I can play with scale to make that work out differently, but I'm not going to bother. All right, you talked me into it. So if I change it to scaling equals constrained, then it will make an ellipse look like an ellipse. So if I look down the barrel, now it's looking like an ellipse where it wasn't before. And that's just a scaling factor. So scaling constrained makes it so the values on the axes all use the same scale. So an ellipse will actually look like an ellipse, for example. But it's this tiny little graph in this huge expansive area, which is always cracking me up. All right, so let's go back and look at this last one. So t comma t comma t squared. So it's up to us which way we want to think of one, because they're both linear, so just kind of pick one. Sorry, both linear, so just pick one. I'm just going to pick the middle one because I've done the other two as an example. I did x as a linear on this one, and I did z as a linear on the other one, and z wouldn't work anyway. So I'm just going to pick y equals t to be linear. So linear stretch in the positive y direction. As opposed to the last one, which had a stretch in the negative x direction. All right. So then what are we graphing? Sorry, my dog is barking, if you can hear that. All right, so t and t squared. So if I look at x equals t and z equals t squared, that would be a parabola, right? That's z equals x squared, which is a parabola. And I need a place to start, so I'm just going to get a point. I know I said I was going to get points in the other one, but it's just not worth my time. I just did 1 point. So I'm going to do 1 point right here. So if I have t equals 0, that would make that r of 0 is 0, 0, 0. Well, that's exciting. That's the origin. So that's pretty easy. And then if I want to do, I don't know, r of, if t equals 2, for example, then r of 2 would be 2, 2, 4. So over 2, out 2, up 1, 2, 3, 4. So it'd be like right there. And you could keep going. Like, what if t equals 4? That would be, oh, I better not do 4. That'll be too big for my grid. Let's try 3. So 3 would be fine. So r of 3 would be 3, 3, 9. So out 3, over 3, up a whole bunch. And so what you're doing is drawing a parabola, but it's stretching that parabola into the 3 space. So it's a little weird, but it can be done. And now let's look at it in Maple. Hold on, I've got to get Maple open. There it is. So I only was graphing half of it, of course. Oh, and I should say that the standard way of graphing in Maple is a box. If you don't like that, you do axes equals normal, and then it'll graph it with the normal axes that you know and love, right? So we were only seeing a very teeny tiny section of this down at the bottom. And of course, there's a backside as well. So there's a piece that matches it over here, right? Going into the other space. It's hard to see, but it's coming out into this quadrant and going back into that quadrant. And then its orientation we also need, right? So we need arrows. So how is it moving? So it's moving this way, right? We can tell because of the points we've picked. We can see that it's going along that direction. So it's a parabola that's stretched in the positive y direction. So we can say it's a parabola. Oh, yeah, I've got it right here. Stretched in the positive y direction, and it has an orientation right. It's implied with the stretching. So the positive y is where it's stretching, so that's why it's going to be moving that way. So orientation from negative y to positive y values, for example. And of course, if we restrict the domain, it would only be like a section of this parabola. But since there was no restriction on the domain, it's the whole thing. And so we're moving along that path, that parabolic path as it's stretched in the y direction. And again, you can really see it in this graph, right? You can see that it's being pulled out. So there you go. We've graphed by hand and with Maple. And the last couple of pages, there's really not much to say because I've already graphed them in Maple for you. So it's using the space curve command. You can see those are the commands. I might have played with these a little bit. They might not be exactly what was written there because I like to mess around with the graphs. So you can see, again, here's that circular one. Oh, look, it's not a circle. So that particular one should be an ellipse, and it's not showing up as an ellipse. So to make that happen, you would do scaling equals constrained. That's one way to do that. There's other ways to do it, but this will be easiest. And there we have The scaling's constrained, and now it looks like an ellipse, just like we expect it to. That wasn't in there, but that's how to make that happen. If we want to make this curve, which we will be seeing later, that's called a hyperboloid when we make it 3 dimensions. So it looks like a Pringle chip, but we're just doing the outline of it right now. So that'll come back to haunt us later. So it looks like that. And I'm making my thickness larger than it is in the notes because I want to be able to see it. So if you look at the ones in the notes, they're really thin. That's because they were the standard thickness. If you don't put a thickness in, it draws them very thin. So I wanted to be able to see them, so I did that. And then down here is the last one, which looks like a jumbled mess when you look at it from the side view. But if you look at it from up above, it's starting to take a little different shape. And that's the beautiful thing about being able to do this in a computer, which is that you can orient things how you want by playing around with the picture. There's also pieces over here with orientation and other things like that. So you can mess around with your orientation, you can mess around with your views over here on this side if you'd like. But just make sure to try to fit into the code if you want it to be permanently part of the sheet. It has to be in here in this code for it to be there every time it runs. And the space curve command, as you can see, I should have mentioned one more time, is the curve command we're using. But you have to use vector notation when you're doing it. So the space curve gets a vector notation for it. And I didn't need to load that vector notation. It knew what I wanted. So just with plots is all I need to make all of this work, because space curve is a plots command. So I load that menu and it will know what I want for space curves, that is.